Okay.
All right. All right. There we go. Okay. So, hi everyone. We're really excited to have Hugh Morton today, who's going to be telling us about framing and not invariance.
Okay. Well, thank you. Thank you very much. And an enormous thanks to the organizers for arranging this global Lou Fest over uh, however many continents it involves. Um, I'm really going back a little in time for a start. Um, Framing and not invariance are things that have come out of work encouraged, you might say, by Lou, or suggested not directly, but over the course of the years. Um, I have known Lou for quite some time now. My first meeting with him was in 1979 in Bangor, North Wales, and it was being organized by Ronnie Brown um, for the then very important work of Bill Thurston and other things of that sort. But Lou was at that point already marvelous at thinking of memorable ways of going from geometry to algebra and back again. Um, he showed me a really nice, quick calculation of the Conway polynomial from a spanning surface, and it included a proof of invariance. Now, at that point, Alexander polynomials tended to come with a little bit of uncertainty, a power of t, and this thing just hit it on the nose so beautifully and very simply. Um, we did continue after that with correspondence. We, of course, correspondence in those days was by letter. It wasn't by email. It wasn't. It wasn't instant. Um, and here was a letter that Lou sent in 1984, around and about the beginnings of the Humphrey polynomial. Um, we had both spent time separately in Spain earlier in 1984 with Jose Montesinos, thinking about fibered knots and uh, things of that sort. But Lou's letter, really, he's saying there, the most exciting thing right now is the Jones invariant, which he was talking about in two variable terms as the Humphrey polynomial. Um, Lou had a marvelous way of informing other people and talking with other people. Uh, right from then, his marvelous notebooks would show up at almost any opportunity. And he has retained this knack of recalling things almost at a drop of a hat uh, and thinking of the most effective way of explaining them without needing any prior warning. You can ask him a question, and the right bit of stuff will be jotted down on the notebook almost immediately. Um, this has gone along with his marvelous use of diagrammatic combinatorics and really memorable rules. Of course, one of the prime examples going right back to this time was his formulation of the bracket polynomial and the relationship to the Jones polynomial and the temporally Lieb algebras. But in the explorations and inventions that followed hard on the heels of the Jones polynomial in 1984, Lou made one very nice observation that there was a great advantage in separating out the effect of Reidemeister one move from all the others. And he called this regular isotopy. Now, regular isotopy keeps recurring. There was this is a copy of notes that Lou had photocopied and sent. If you see Hugh, paper to follow best, Lou up at the top there. Ooh, no, that won't work. I'll get rid of that. But this is, he was talking about the generalized polynomial of Jones, etc., the Humphrey polynomial in those terms. And at this point, he was talking about the use of separating out Reidemeister one move from the others by using bands around the knot or link. In other words, he was what we would say now, he was talking about framed links and the framing. Now, framed links, that is to say, it's a link with a preferred annulus around each component, which is another way of talking about the framing. But in most cases, these are the natural building blocks of interest. A choice of framing is often needed if you're going to make constructions based on a link. You want to choose a framing. And one subsidiary consideration then for your invariants is what happens when you change the framing. Lou managed to reformulate the Humphrey polynomial for a framed link in a way that, going back to that thing about the use of bands, it really made it look combinatorially just like the Conway polynomial from years back, with one added parameter for the framing change. So here was Lou again talking about it. Well, he's called it the R polynomial. That's Humphrey with framing in mind, and he has got these two. He's got this move 3. If I can just show it up, that is the Conway-Skene relation. It looks like it, but it's subtly varied by the framing. As you change the framing, as you put in or out a curl, there is another parameter. In his case, he's called it alpha. I was looking at similar things then, and my parameter was V, which is alpha inverse, but similar sort of thing. And this description of the framing meant that you were able to summarize it by these Skene relations. Conway-Skene relation at the top and the framing change at the bottom. And it all worked very nicely. Sorry, just now at the same time on this great beginnings of things, 1984, 85, whatever, Licorice, Millet, Brandt, and Ho came up with a polynomial to do with unoriented links. And they said, ooh, 3-term frame relation, that's not enough. Let's have a 4-term Skene relation. And they had this polynomial Q, one variable polynomial, depending on the parameter Z, and the Skene relation that would tell you what to do when you swapped over a crossing. Now, people know very little, I think, about the polynomial Q, because Lou managed to treat this as a relation on framed links and put in an extra variable and get a 2-variable polynomial out of this, almost what looked like the same ingredients. He added the extra variable for the change of framing along in the same sort of way that the Homfly did. And he put in the extra parameter. And you've got Kaufman's two-variable polynomial, which is a great thing. It's even better in the Dubrovnik form, where you've got the minus signs in because it tallies with other things. It underpins construction of various algebras. Berman, Wenzel, and Murakami made use of it to construct an algebra that was a bit like the Hecke algebras in their relation to the Homfly polynomial. And this Kaufmann polynomial has rather remained in the background compared to the Homfly. From some points of view, it's to do with the BCD series of Lie algebras rather than the A series, but it's slightly second layer. And while it's remained in the background, there is, as always, the question of if you come across a new invariant, can you express it in terms of previously known ones? In a way, that was sort of John Conway's principle. A little diversion here. John Conway, I would say, was the father of skein theory, the Conway polynomial, etc. And he had the knack of finding really simple, memorable terms for lots of his ideas. The terms skein, tangle, mutant are all due to Conway in the first instance. Skeins, by the way, come from the term in knitting. People have skeins of wool, a loosely coiled length of wool. Now, Conway used to say, you ought to do two things when you come across a new invariant. You've really got to show that it distinguishes a couple of knots that can't otherwise be told apart. Otherwise, well, how do you know it's new? It might be something that you've already seen in another guise. And then you've got to produce two knots that it can't distinguish so that you can continue the fun. So an early exploration along these lines for the Kaufmann polynomial was due to Lee Rudolph, who tried to, I would say, tried to find it from the Homfly polynomial, at least tried to relate it to the Homfly polynomial. Now, of course, the Kaufmann polynomial of a link doesn't depend on the orientation of its various components. In Homfly, if you change the orientation of all of them, nothing changes, but you can change one and not the others, and then you'd get something different. But Rudolph started with a framing for the link and thought of looking at the Homfly polynomial of the reverse parallel. That is to say, on each component, you put one string oriented in one direction and a parallel string in the opposite direction. And this, of course, doesn't depend on the orientation of the original knot. And he, to some extent, he nearly recovered the Kaufmann polynomial this way. He did a very neat bit of hands-on skein theory that is sort of hidden in the archives, you might say, that he showed after a little bit of normalization and correction factors, he could retrieve the Kaufmann polynomial, but only with the coefficient mod 2. So there's an awful lot of stuff that he couldn't retrieve, but there was a connection. I've looked in terms of subsequent connections to quantum group invariants to try to really get a bit of an explanation of the mod 2 connection. Doesn't entirely work, but few years ago, Nathan Ryder and I did find a good framework for some similar relations between the more general Kaufman, colored Kaufman, and colored Homefly, which I'll say a word or two about at the end. But just back to framing, Lou's focus on framing is something that gives you a simple but really crucial perspective for some invariants. Like Lou's version of Homefly, the various irreducible quantum group invariants, which then turned up, they've all got what I'd term, for want of a better word, the scalar framing property. That means defined for a framed link, and if you change the framing, increase the framing by 1, then the invariant just gets multiplied by some fixed scalar, depending on the invariant itself, but not depending on the knot. And that is somehow a very central feature of a lot of invariants, or ones that are useful to focus on, that they have this scalar framing property. So might say that part of Rudolph's work was involved, his correction terms and so on, were to try and deal with the framing behavior for the Homefly polynomial of a reverse parallel. If you take the reverse parallel and then put a twist in the knot, you don't get a scalar multiple of the one you started with. So it doesn't match cleanly with Kaufman on the nose. You've got to do a little bit of work for that. His solution turned out, in effect, to write the Homefly polynomial of a link with a reverse parallel on a component as the sum of 2 invariants, each of which separately had the scalar framing property, but different framing scalars. And one of those was the one that really matched neatly. So as a reprise, let's think about the reverse parallel. It's a good example of a satellite. We've had various comments about satellites. They're very much at the geometric heart of things that go on. So they're always good testing ground for how your invariants that you're looking at or your constructions are going to behave. So a satellite, you start with a framed knot K, or framed link, framed knot, let's say, and you decorate K with a pattern, which I'll call Q, and a pattern is simply a diagram in the standard annulus. The first one there is the, that's not going to work. First one is the Whitehead double pattern. Second one is the reverse parallel pattern, you can see with the orientation. And then you place the annulus with the pattern in it around the chosen framing neighborhood of the K. And that carries the diagram Q to the satellite, which is variously noted K star Q of the framed knot. So if you start with, there is K as a framed knot with the blackboard framing, and you take the Whitehead double pattern, then that's what you get as a satellite. And of course, similarly, the reverse parallel pattern follows like that. Now, if I move on a little bit, I suppose when I'm thinking about satellites, one of the natural things that you can do with a satellite is if you've got an invariant in your mind, Homfly polynomial, for instance, or something like that, and you're looking for new invariants of your not Q or not K, anytime you have got a pattern Q, you can treat the Homfly polynomial of K star Q as an invariant of K, depending on Q. So you've got a whole slew of new invariants based on the same original invariant. And these are sort of the satellite invariants of the knot K. And my favorite object for handling satellite invariants, such as the reverse parallel, is to look at the skein of the annulus. Now, the skein of the annulus, if I'm thinking of the Homfly invariants, I want the Homfly skein of the annulus. If I'm thinking of the Kaufman skein of the annulus, then those are the ones that come up in the Dubrovnik form. So the skein of the annulus, in short, is linear combinations of framed diagrams in the annulus, subject to the Homfly skein relations on the one hand, or the Dubrovnik skein relations on the other hand. And these two skeins are individually, they're linear spaces. They organize the combinations of diagrams that are used for making satellites, and then the resulting colored Homfly or satellite Homfly or colored Kaufman invariants. And they're really a very great help in, and have featured for years when you're looking at even quantum group invariants that on Conway's side of things, they cover the same ground, but maybe in a slightly different way, but they tell you exactly where to go. So one of the nice things that you might be looking for in these skein invariants, in these satellite invariants, is, again, ones with the scalar framing property. So that when you put a twist in the pattern, you just untie it around a knot, you just get a scalar times what you originally had. This is particularly the realms where you get a neat correspondence with the various quantum group invariants based around the, around the A series of Lie algebras, the SLN series, or B, C, and D, the various orthogonal and the orthogonal group series of quantum groups. And when the quantum invariants are in mind, particularly, it's useful to be using the variable z, using a different variable s, with z equal to s minus s inverse. I've used v here rather than alpha. This was my lot. So you use the coefficient ring integer Laurent polynomials in V and S, and for various technical reasons, you find yourself with quantum integers that have to be inverted. So you allow the inversion of these elements s to the r minus s to the minus r. But this is, I don't want to do too much technical detail on this lot. I'm going to tell you about things rather than writing out all the details, which I should say are, I'm not talking about stuff that I have done last week. I'm talking about things that have come a few years back along the line. But certainly in the case of the Humfly skein, there is a very nice basis consisting of elements Q lambda mu with the scalar framing property. Scalar framing property doesn't uniquely distinguish these elements. There are some other even better properties that do, but the basis, these elements Q lambda mu, they are correspond with two partitions of an integer. Lambda is a partition of a non-negative integer, which is written as mod lambda. Mu is a partition of another one. And you could, lambda might be a partition of 4 that is 3 plus 1. Traditionally, people draw them with Young diagrams and so on, and mu might be 0, so there's the empty partition, you might say, in that one. But these elements Q lambda mu are very nice. If you take any diagram in the annulus, which would be representing an element in the skein of the annulus, if the diagram meets a transverse arc on the annulus in n points in one direction, p points in the other one, then that can be expanded as a linear combination of the elements Q lambda mu with just partitions of less than or equal to n, less than or equal to p, and the numbers mod lambda and mod mu being the same as n minus p, which is just the winding number of the diagram around the annulus. If you start off with the Whitehead diagram that we had a little while ago, or the reverse parallel for that matter, and you take an arc across it, you can find an arc that meets it. The diagram meets the arc once in one direction, once in the other direction. And if you go back to what I'd said there, it can be written then as a combination of the basis elements Q lambda mu with lambda and mu less than or equal to 1, and lambda mod lambda minus mu being n minus p, which is 0. So the only possibilities there are lambda is the partition of 1. There's only one partition of 1, and mu is 1 again, or 0 and 0. And these two basis elements, they've got scalar framing property, each of them. Framing factor is v squared in the first one, and just 1 for the second. 1 is really only a scalar. Now, Rudolph's result had identified the Dubrovnik polynomial of a link with the Humfly satellite invariant, which uses the skein element Q11 on each component. And it does that after replacing v and z in Dubrovnik by v squared and z squared. But you're stuck only with getting an answer mod 2. As a diversion, I keep remembering the quote from R.H. Bing about integers and integers mod 2, which was that God made the integers and the devil made the integers mod 2. So Yeah, just be wary of mod 2. Now, quite some time later, Ryder and I, Nathan Ryder and I, turned up with a similar result about the general colored Dubrovnik polynomial, which depends again on the use of a basis in the Dubrovnik skein with the scalar framing property. There's a nice basis due to, I think, Belyakova and Blanchet, a basis y lambda, where lambda is just the partition of a single non-negative integer lambda. If the non-negative integer is 1, then the partition of that is just lambda equals 1, and the element is just the single string, the original Dubrovnik polynomial. But in this skein, a diagram in the annulus that meets a transverse arc in R points, that can always be written as a linear combination of the basis elements y lambda with lambda less than R and an even number distant from the original R. Now, if you are thinking about the general colored Dubrovnik polynomial for a link, what that amounts to is you can expand it in terms of these basis elements, and it all boils down to saying, well, you've got to choose for each component of the link Li, you will have a y lambda I, different, not necessarily the same for each component Li. And there is a very satisfactory relation of this to the Homfly polynomial, the colored Homfly, in that if you start off with a general colored Dubrovnik polynomial, you've got a lambda I for each component Li. So where you've used y lambda on a component, just replace it by q lambda lambda in the Homfly skein of the annulus, then calculate Homfly. And we'd again finished up after a bit of circuitry, showing that, with coefficients modulo 2, this with q lambda lambda on the Homfly skein, that gets you the colored Dubrovnik with lambda in the right place. Once you've replaced v and z by v squared and z squared, or, I mean, equally if you're working with the s, v and s by v squared and s squared, and you have the coefficients mod 2. So it was a very satisfactory result, but there is, of course, a lot of difference between what you get with integer coefficients in each case. And I've never really come across a nice, satisfactory analysis of what it is. Because a lot of the time, if you're using Homfly skein with a q lambda mu, and then you've got, and lambda and mu are different, then you've probably also got q mu lambda around, and they will give you the same sort of answer. And when you add the two together, you get something that is 0 mod 2, so you don't notice it. So I thought that I would just really come to fairly much full circle. 40 years ago, this Homefly polynomial has been around. On the back of that letter that Lou had sent me in October 84. Oh, by the way, I discovered I wrote back to him. It wasn't by return of post. It was December by the time I'd written back to him, because, as I said at the time, I was busy teaching and all sorts of things. But it then turned up. But on the back of Lou's letter, he'd written something like this. He'd been trying to work on things about the Jones polynomial, but the key thing there is this is the most exciting development in knot theory and its relation to algebra and combinatorics that I have ever experienced. And I think he has shared that enjoyment with an awful lot of people over the years. At the time, people were managing just about to calculate Homefly polynomials of things and work out all sorts of fun. Jim van Buskirk, who was an old-style knot theorist there, he said this of Homefly: "I don't mind if I never get a theorem out of it, but I haven't had as much fun in years." And I think that goes along with Conway's idea of maintaining the fun. Lou has certainly helped us continue that fun for the last 40 years. The number of people that have been involved in this meeting give testimony to just how broadly he manages to enthuse people. So I think at this point, I know I maybe haven't given you full value, but I think I would like to finish by saying happy birthday to Lou. So, all done.
Great.